So that introduced, the idea of adversarial search. So, so basically, there's two types of agents. The agents denoted by upward pointing triangles will be a maximizer, and then the downward pointing triangle will be a minimizer. And this basically is a process of like maximizers thinking about how the minimizer will act, and minimizer in that thinking process thinking about what the minimizer will act, in response to how the maximizer will act, so on and so forth. So you can see this recursion is possible, but let's formalize it, a little bit before, formalize agent search a little bit before we dive into, the adversarial search. So in a single agent setting, there's only one agent that's able to act. So in this case, the Pac-Man can move left, which will give, which will make it into this state, and you can also move right, which will lead to this particular state. And then from each of those states, you can either choose to move left or right, and you will get, these four successors here. And then you can, go down from here. Let's say, if the goal for this game is to eat the dot, then, this state in particular here, it's a terminal state, which means it will no longer go, it doesn't have any successors, and it will not be expanded anymore. But, the other three, you can imagine, can continue to go down. So this is basically, an example of a single agent search tree. This is similar to, the BFS and DFS, and then, A star, all those stuff, the settings where those algorithms will be applied to.
And then you can see that there's a value associated with each terminal nodes. And we consider the value of a state to be the best achievable outcome or utility from that state. So at terminal nodes, it just means that, okay, if I finish all the dots, it means I'm in a very good state, so I will have a higher utility, and vice versa. Whereas for non-terminal states, we consider the value to be, since the definition is the best achievable outcome, so we would take the max over all the successor states from that current state. So we will assign the value of the current state to be the max of the value of all successor states. And that's for single agent. So let's take a look at what adversarial game trees look like. So imagine Pac-Man, it's blue, and the ghost is red. So Pac-Man tries to eat a dot, whereas the ghost tries to get Pac-Man. And from the top branch, Pac-Man is trying to make a decision. So it can go either left or right. So after Pac-Man moves, now it's the ghost's turn, and ghosts will also try to make a decision, or either go left or right, and then so on and so forth. And then at the end of the adversarial tree, you will have a bunch of terminal values. So notice the difference here. You have two types of nodes in this tree. Blue nodes corresponds to the maximizer, which is Pac-Man. And the value of that maximizer is going to be the max over all the successors, because it's trying to do the best at, it tries to maximize the utilities. Whereas for ghost states indicated by red nodes, they will try to minimize the successor states because try to minimize the utilities. And the terminal states, the value of the terminal states are just the number, which is the utility of those states.
Yeah, and then we can think about a more complicated example with tic-tac-toe. So in this particular case, it's a pretty big branching factor, but as you see, we go down the trees, and there's really only three possible outcomes: the maximizer winning, the game reaches a tie, and the minimizer winning. So we basically assign numbers +1, 0, and -1 to those three scenarios. And in this particular case, you can see that the maximizer, which is the one that wants to win, will always try to minimize the terminal utility, whereas the minimizer wants to minimize that utility because the minimizer wants to win.
Okay, so now you've seen those examples. Basically, it boils down to how do we perform an adversarial search so that either the maximizer or the minimizer can try its best to do its job. So what they do is actually calculating values. The values are calculated recursively. So for example, if you're at a maximizer, you would look at all the minimizer nodes, and you would call the minimizer to compute the utilities at those nodes, and you would take the max of all the computed utilities. So in this case, if the maximizer tries to calculate the value, it will look at the first minimizer, and it will predict what the first it will calculate what the first minimizer is. So the first minimizer will pick between 8 and 2, so we'll get 2, and then the second minimizer will get 5, and then the maximizer will look at those values and say, okay, I want to go to the right branch because I have a better utility there. And if you have a deeper tree, it will go. The process will continue. So, and here's the implementation. So if you're at a maximizer, you would initialize your value to -infinity because you try to maximize it. And as you go through each of the successors, you will call the minimizer, which is basically another function that does the job recursively, and you update your best value accordingly. And it's kind of symmetric to the max value function. The minimizer will initialize the value to the infinity because you try to minimize the value as you go through each successor states.
Yeah, and then we can see that these functions, they call each other, in some recursive fashion, and they actually also correspond to, the formula you saw in, I think, a few slides earlier. The maximizer is going to compute, the max over all successors, and the minimizers compute all the min over all successors. Mm-hmm. So I guess this is, just a slightly more general implementations for the min value and max value functions. So it's basically just to define a value function, and if that's the terminal state, you return the terminal state's utility. And if it's a max, if the agent, is a maximizing agent, you return the max value. If it's next agent is a min agent, you basically you call the min value functions. All right, so let's go over Minimax example. So the root node is a maximizer. And then it will call one of the minimizers. So the minimizer to the left has value 3, 12, and 8. So what should be the value for this for this minimizer?
So we'll pick 3, and then the maximizer will look at another minimizer here.
Right. So the second minimizer will have the second node for the minimizer node will have 2, 4, and 6.
So we'll pick 2. Sorry, my 2 is a little bit curly.
That's fine. So then we look at the third possible outcome for the minimizer. So it's going to be 14, 5, and 2. What's the minimizer going to pick here? 2. So now we have all the successors of this maximizer node computed. What's going to be the value here?
They're going to take the max over the 3 values and return 3. So notice that the order in which we traverse the tree, right? So we go down to the leftmost branch, and we look at a bunch of utility values, terminal values, and then we return to the minimizer. But that value doesn't go to the maximizer yet, because the maximizer has to go over all the successor values before it picks the best one.
All right.
All right, let me clear my drawing real quick. All right.
Okay, so I guess the key assumption here when we are performing Minimax search is that we assume our opponent is playing absolutely optimally. So in this particular case, we can see that the way this search tree is constructed, we should, we know that this minimizer is going to take on value 10 because it's taking the minimum value between 10 and 10. And here it's going to be the minimum between 9 and 100. That's going to be 9. So the maximizer, if we assume the opponent is playing optimally, should take this action because 10 is strictly greater than 9. But if the maximizer pick the other option, then as long as the minimizer mix up a little bit, then the maximizer could get a lot higher reward. So okay, so let's say you are playing with this super expert opponent, then you probably are better off playing the safe move. However, if you're playing against this very amateur and maybe less sophisticated opponent, maybe you can assume that they might make some mistake, and maybe going the other direction will give you actually more reward. But I think in this particular I guess in this particular discussion we're having about Minimax, we are assuming that the opponent plays optimally.
So we should choose 10.
Yes.
All right, let's go over another example in Pac-Man game. I think you need to be muted.
Nature we're about to put Pac-Man in. So
yeah, so basically this setup is Pac-Man with 2 ghosts, and as you can see, Pac-Man is in a very bad position. So what would you do? What would Pac-Man do if it's a Minimax agent?
I think it's going to run straight into the ghost, right?
Yeah, because every move costs Pac-Man some score, and if Pac-Man knows it's gonna die eventually, why doesn't it die very early to avoid any further penalty? However, if the ghosts are actually somewhat random, the Pac-Man might be able to choose something differently. So if you look at the blue ghost, it can actually go up or down. And if it is optimal, of course, if it's like a minimizer, then it will definitely go up. But if it's somewhat random, it might go down. So Pac-Man might have a chance by just giving it a try and moving left. As we can see here, so if the ghost is a random agent that doesn't play optimally against Pac-Man, almost there. Okay, so after first time step, the ghost actually went to the other direction. So in this case, Pac-Man wins. But again, our previous discussion involves only the minimizer playing optimally against the maximizer. So this scenario can never happen in that discussion.